welcome Professor Mary McHale from the chemistry department. Mary is a former teacher at Rice University and has been teaching chemistry here at the college. And I want to thank Nishi for bringing Mary to CAP to make her presentation. Mary's title today is Silver Nanotechnology, Doorway to Science Education and Practice-Based Learning. Thank you.
Thank you. I know English. What do you teach?
English is a second language and education.
Oh, I have a funny story. When I was doing my PhD over here, they said, "You're an alien, aren't you?" And I said, "Yes, I'm an alien." So that means you have to take test of English as a foreign language to do your
serious?
PhD. And I refused.
Are you serious?
I
That
truly
was an
refuse.
ignorant person. Oh my God. Oh my God.
So math,
The right is in the right place.
right place. I know, and I know. Sorry, what do you teach?
Kinesiology.
Kinesiology. Okay.
So-
So anyway, I
Okay.
developed this silver nanotechnology protocol as a doorway to science education and practice-based learning in a desire to inspire students to go into sciences, physics, chemistry and biology, technology, engineering and mathematics, the numbers that are decreasing. And in order for me to be able to give this talk, I need to recognize two other people. Alvin Orbach, who was a graduate student at Rice. I retired from there a couple of years ago. And his research mentor, Andy Barron. I was actually talking to Alvin, and I was saying, I really want to have something that excites the students. It captures their imagination, and I want to do it across the teaching levels, because I used to do a lot of outreach K through 12, not only the freshmen and organic labs as well, and the lectures. So that was my desire in setting up this protocol. And I hit on nanotechnology because it's been the buzzword for the past 10, 20 years. And the good thing about nanotechnology is it encapsulates a lot of the sciences. It encapsulates chemistry. In the method I'm going to talk about, you need chemistry to make the nanoparticles, and then you need physics to understand what's going on. And then if you use it for any sort of bacterial work, that will involve biology as well. So it is all-encompassing. This is my favorite saying, and I'm going to read it in its entirety. And it's from Albert Einstein. Imagination is more important than knowledge. For knowledge is limited for what we know and understand now, while imagination embraces the entire world and all there ever will be to know and understand. I used to say that a lot to my students, but it used to come back to bite me, because when I asked them, you had to make this organic compound in 5 steps. And if they got lost and couldn't make the compound, from the 4th to the 5th step, they would say, and a miracle occurred. And I told them that was too much imagination, not based enough on fact. So I did actually try and temper the number of times I said imagination is more important than knowledge. But anyway, I got involved with the American Chemical Society Project Seed Summer Research Program. And it basically was for introducing disadvantaged students, and by disadvantaged students, it's the ones that we consider that are not going to finish high school. And generally the reason they don't finish high school is because of their math, and then chemistry is the second on the list. And so we developed, must have been about 15 years ago, an enrichment program for the chemistry students. We had math at Rice for the past 20, 25 years, but we developed one for the chemistry program. And we have got this seed project, and we wanted to capture their imagination with nanotechnology. A little bit of history that you probably are all aware of. The buckyball is the third form of carbon. We all know about the first two, which is graphite in your pencil, and diamond, which is the hardest known substance. Well, in 1987, 3 scientists, Robert Curl, Richard Smalley from Rice University, and Sir Harry Kroto from Sussex University in England, discovered that there was a third form of carbon, which is 60 atoms fused together. It was given the technical name, where's my mathematician, Buckminster fullerene, and that describes the shape here, where you have 12 hexagons and 12 pentagons and 20 hexagons. I always say that wrong. Basically, it looks like a soccer ball. And instead of saying Buckminster fullerene all the time, it was abbreviated to buckyball. Do I have any native Texans here? Okay. You realise you are the only state with a state molecule. Texas is the only state with a state molecule. And that is the buckyball.
Oh, because the smallest two are that.
Oh, yeah.
Oh, so good.
So they discovered this in, I think it was 86 or 87. They didn't get the Nobel Prize till 97, because everything takes about 10 years for scientists to say, oh, this is really cool. Let's give them a prize. But anyway, when you take your buckyball and you elongate it, you get something called a nanotube. Looks like chicken wire, doesn't it? But I have my show and tell. This is my prized possession. This is my snow globe, or my carbon nanotube globe. And as you can see, as I'm shaking it up and down, it is very light and fluffy. If you'd like to pass it around. It is 100 times stronger than steel, because we're talking about nanoscale properties. It in fact conducts electricity 4 times better than copper does. So it really has wonderful, unique properties, and if we can show that, which I did every magic show I did, to students, then it inspires them, and they think, oh, science is cool, it's not boring and dull. So anyway, it allows you to make a lot of different things. There are now end of things that can be made using nanotechnology. It has lots of interesting properties. I've said about it being extremely strong. The SWNT stands for single-walled nanotubes. That's the main of the research that you use, single-walled nanotubes. Quantum dots, what they are nanocrystals using semiconductors. There's a myriad of things. I could go on ad infinitum. But the thing to appreciate about the nanoscale is the fact that you've got a lot of surface area exposed. And if you've got a lot of surface area exposed, it's going to be very reactive, and you're going to get some unique properties. And this is a slide that we used to use to show that the bulk gold is not size dependent. When we get down to the nanoscale, we can get any color that we wish, depending on the size of the atom that we use, from red to purple to goodness knows what else. Here actually, it was mentioned before we started the talk about gold nanoshells. Gold nanoshells have been used, I think, for about the past 10, 15 years. I know that the people that were working on it, Naomi Hallis and Jennifer West, they looked at the different properties at the nanoscale of different gold nanoparticles. And I've labeled here, if you have 3 nanometer size, you'll have the red color. If you go down to the 2 nanometer size, you'll get this sort of sludgy brown color. Now what they did with it is they actually put the nanoshells into rats to target cancer cells. And when you put them in the rats and shine a laser outside, it will destroy just the cancer cells. Most of the problems with chemotherapy is you destroy good and bad cells. You can tell I'm not a biologist. So you destroy both of them. But here, you're targeting just the cancer cells. This has gone from rat trials to human trials. So it is important. But it's only for one type of cancer. It's not a one-shot cures all. I mean, there's all different types of cancer, so it's a good sign for one thing. And I did mention, for my mathematician, that we can make them look at the increased reactivity at the surface. When we do some calculations, if we have a very small size of 2 nanometers, and I should say for everybody, nanometers means 10 to the minus 9 of a meter, so in other words, very tiny. If it's 2 nanometers, you've got 64% of the atoms on the surface. And I bring this tennis ball along because it's very difficult for people to think about atoms. And if you hold this up and say, imagine it's very much smaller, you can see that you've got 64% of your atoms. In other words, half of the surface is covered with your atoms. Whereas if you go down to the 300 nanometer size, you've only got 1% on the surface. So that's going to be much more reactive than that, isn't it? The nanotechnology applications in general that we've known for quite a long time are the self-cleaning windows that you can have. I want a house with self-cleaning windows. Basically what they do is they put a glaze of titanium dioxide on the windows. And the titanium dioxide has two properties. It's photocatalysis. It will break down the dirt when it hits your windows. And then you've got the hydrophilicity. So when it rains, the dirt will run off. Beautiful. I don't know how much is readily available, but it's a good thing to have. Now, the stain or wrinkle-free clothing, you can buy it in shops. I wanted it for my son when he was younger because he was forever spilling his whole dinner down on himself. But anyway, there are problems with it because most of the time you use nanomaterial that uses the lotus effect. In other words, the dirt will bead up on it and then be brushed away. Well, it breaks down. It breaks down under duress. If you have a lot of rain, it won't work at all. If you put it under a lot of stress and strain, it won't work at all. Now, the Harvard professors have come up with something called SLIP. And I haven't a clue what that stands for, but, sorry, I should have had that ready. But basically what that will do is an improvement on what we used to have in the fact that not only will the stuff run off, it will also self-clean. So you won't need any washing machines anymore.
This is maybe, I noticed about 5 years ago, I started buying some white shirts that when they come out of the dryer, they look like they've been pressed by a professional.
Yes. Yeah.
And it was just this huge jump in.
Where did you buy those?
Yeah, they're absolutely stunning. Yeah, I get them. Most stores have them now. But they look like they came from the laundromat or the laundry, where they pressed them and they look. And the 5-year-old ones are starting to wrinkle a little.
That's not bad after 5 years, as I will tell you.
Yeah, so because I wear these things once a week,
So the slips that the Harvard research team have got are slippery, liquid-infused porous surfaces. And so it's wearable, it's stain-free and self-cleaning. No washing machines. Pregnancy tests, of course, use gold nanoparticles. They're on the little dipstick that changes, it binds with the protein. That's as far as I'm going to get into biology. It goes over my head. Great. The Sol Fresh socks, the silver nanoparticles I'll talk about because we actually did an experiment washing 4 different brands because they're sold for diabetics and they're also sold to people in the army if you're in a war zone and not likely to change your socks for a few days. It enables the person to still stay by the side of you because it kills the odor and it kills the bacteria, supposedly.
Okay, but silver is antimicrobial.
Yes.
But with lots of surface area.
The other thing they're doing is they're using carbon nanotubes to replace your Kevlar vests. The Kevlar vests, if you've ever seen a policeman on a hot Texan day, he's sweating buckets because it's not only heavy, it's uncomfortable. Well, if you think about it, carbon nanotubes will be 17 times stronger than Kevlar. We've actually done tests at Rice. Somebody went off to a shooting range to see how much the normal bullets through Kevlar and to the carbon nanotubes would work. And one nanotechnology conference a few years ago had a whole t-shirt made of nanotubes, which means if you're an undercover cop, you've got a certain amount of protection, haven't you? So it's good things coming. The sunscreen we've known about, the zinc oxide and titanium dioxide, if you want to look like a whiteout, that uses titanium dioxide macro size. When you use the nanoparticles, that's where you get the colourless sunscreen. So that's a change again. And if you wanted to look at, sorry?
Are those sunscreens available with nanoparticles?
Yes, and that is a bone of contention because some people are saying, how safe is it? Because if it's nanoparticles, it can get into your pores and things like that. So that is an ethical issue to consider.
Well, I was wondering about all of that, about is any of it dangerous for humans?
Jury's out because we've only really been playing with this stuff for the past 10, 20 years. So the jury is out on that.
And none of these are drugs, and nobody would have had to have done a trial.
Exactly.
Except probably for the sunscreen because it's applied.
No.
But it's not a drug.
It's not a drug, so yeah. you
So
can
nobody has actually
get under the
done
counter with that.
those billion-dollar trials that for the iron-free shirts.
Yeah.
Now, as far as the Teflon, they said years ago that, Teflon particles get into your food and you digest them, it's supposed to be bad for you. And that's what they're saying, if your Teflon scratches, be careful,
Yeah.
throw it out, don't try to revive it, you can get Teflon in your system.
Yeah.
So it's not good for you.
Yeah. Oh, the reason I got this, King's Chapel, Cambridge, stained glass window up there, I tried to get one from Salisbury, because my favourite book is Pillars of the Earth, and that was about a cathedral that was being built over many centuries. Anyway, in olden days, they used silver nanoparticles and gold nanoparticles. They didn't realise it, but they did, because the ruby red colour in stained glass window is nano gold. The gold colour is nano silver. And I actually did for Girl Scouts and boys a little lab where they could make their own stained glass using PVC and stuff like that. It's a fun lab to do, and they got a merit badge or something, whatever it was. But anyway, they have used it for many years, and now I'm going to go on to Pacific Silver. And as you rightly said, it is antibacterial, microbial, and antifungal, and anti-everything. I didn't know another anti I could use.
Anti-life.
Hopefully,
Oh, okay.
hopefully not anti-human.
So we've known for years about its creams to prevent infections. If you go to your supermarket now, you can buy Band-Aids and they proudly say with silver nanotechnology in it. So, buzzword. We've used it to prevent odours. A good place to use it is in paints in hospitals, hospital curtains to prevent infections. And, excuse me, sorry about that. I tell my students off about that. To silence my phone. The trouble is, if I silence my phone and then I forget to stick it back on again, I get in trouble with my daughter, who's calling me. Anyway, so we're talking about hospital curtains and paint in hospitals. Your lunch boxes, if you have those large coolers, you'll see that you've got your silver lining, silver there, and your refrigerators, air filters have now got it. Wine chalices, that was interesting. The Roman Catholic Church have always used silver on the inside of their wine chalices because they knew that it would prevent bacteria. And if you're having communion, you didn't want to spread the germs. Baby carriages, and then there's optoelectronics that are going in the future. Okay, so getting back to my talk. What we wanted to do is a series of lesson plans. We wanted to do one for the Children's Museum, and that has any age from, I don't know, 6 up to whatever that goes to the Children's Museum. One for high school demonstration, and then for freshman lab. And the lesson plan requirements, basically, being chemistry, we wanted the reaction to be reasonably quick. We wanted the materials to be non-toxic, because if we're going into high schools to do them, a lot of high schools don't have fume hoods. We also wanted students to be able to see the end point without using any sophisticated equipment. In this case, everybody's got a laser pointer. So you can see the end point using a laser pointer in high school. Some high schools actually have UV vis spectrophotometers, so we can follow the lab using that. Luckily at Rice we used a UV vis spectrophotometer, and then there were certain instances washing the silver socks that we couldn't really see the correct answer, so we used a scanning electron microscope to get better information. And we provided the students with details about it. We wanted the materials to be water soluble. We didn't want to have to lug a load of organic solvents around and have nasty cleanup. And we wanted them also to be stable enough so that we could use them for further reactions. And we covered all those bases by doing a silver nanoparticle synthesis. And basically, we used silver nitrate. And if you've ever seen silver nitrate, you should always have it in a darkened bottle because the light degrades it. So we wrapped it in foil to make sure there was no problems with that. Then we used a couple of chemicals, mercaptosuccinic acid, smells, but it's good, and sodium borohydride. Sodium borohydride was what we were using as our reducing agent, reducing silver 1+ to silver metal to make the nanoparticles. And basically what we did is we had 50 mils of water in this Erlenmeyer. We added 10 drops of silver nitrate, 20 drops of mercaptosuccinic acid, and then when we mixed those all together with a stir bar, we then added our reducing agent, which was about 2 to 5 drops of sodium borohydride. The reaction happens pretty fast. You get a lot of colour change. So you keep the students' attention. It's no good having a demo and you're not keeping their attention. And last time we did it was a couple of years ago, and it was the time the Harry Potter movie was coming out, and they all thought it was magic and whatever. And we were trying to convince them, no, it wasn't magic, and this is why it isn't. But we asked these questions because there's no point in having a teaching exercise without asking questions. And we asked what size is nano. Quite often, the parents that were with the kiddies didn't know what that meant. How new is it? Why is it important? What does it look like? Where can I find it? Why does the colour change? And is it magic? And basically, if you use your tennis ball again and say, imagine this is your silver atom, and you shrink it down 10 to the 9 times, in other words, 1 billion times, then think of looking at the stars in the sky, and you can never count them, on a clear night, and if you're not in Houston, because you can never see anything in Houston, think of a nice starry night, knowing that you can never count all the stars, and just imagine you've got that many little tennis balls in that beaker, and that is what all the little nanoparticles would look like. It's difficult getting them down to that small size, or to understand it. Anyway, it worked well. And then the next one, we went to high schools. And when we went to high schools, we gave them this little chart, which is from the Department of Energy. And it nicely compares the scale of things natural that you'll find, an ant is 5 millimeters, down to your DNA, which is nanometer size. And then things that are man-made, the head of a pin, down to here, you have a corral of 48 iron atoms on a copper surface. Beautiful picture. Oh, and there's your buckyballs, which is generally about 1 nanometer in size.
Can I ask
Yes,
a question?
please
So
do.
you're saying the silver nanoparticles.
Yes.
Are they buckyballs or tubes or?
They're little atoms of silver that
So they're
are
independent
shrunk in
atoms?
size. Yes, they're little silver atoms.
So just independent atoms?
Yes,
Okay.
yes. So the, what is it, the diameter of an atom of silver is